All right. Are we here? Yes, sound. Woohoo. All right, welcome back. Ha ha ha. Where were we? Hey Salvador, Said. How are you guys doing? Good morning or good afternoon. I don't even know anymore at this point. Okay. Um, how's everyone doing? Hmm? Hey Andres. Of course you're not missing one single live stream, huh? Thanks a lot for that, man. Muchas gracias. Hey, Dusko. Good afternoon. What's up? You were in the morning as well, right? Good, good. We like that. All right. So, what are we doing this afternoon? So what are we doing this afternoon? We are continuing with what we were doing with morning this morning. Good night in France. You're in France? Okay. So it's about 8 p.m. in France right now, right? All right, so we were here. So remember that I blocked my computer. It took an hour and a half to compute the boundary surface of a level 7 Koch flake. So yeah, don't try this at home. I have a fairly powerful computer, so yes. So don't try this at home. So what are we doing today? We are going to do similar to what we did this morning. This is going to be a Christmas theme live stream. So what we're going to do is we're going to implement a Sierpinski tree. So we're going to implement this fractal shape based on a triangle. We're going to start subdividing this triangle recursively in order to create this Sierpinski tree sort of thing that looks like a Christmas tree, maybe. I don't know. But before we do that, we are going to record the introduction to the second video, the one where I was going to explain how to do the Koch star in C sharp. Okay, because we didn't record that this morning because everything just blocked. So let's do that, and then we can get running with the Sierpinski tree. Okay, and in order to do that, and I'm going to turn off the noise canceling for this one. Okay. No, wait. There you go. Hello, hello, hello. Ooh, this is very loud. All right. So let's do this. Here. Oh, I need to wait. Let me get this. All right, much better now. All right, all right. Ho, ho, ho! Can you hear that? Can you hear the bells? All right, this is a small Christmas theme video. This is the second part of the video that I was working on, which is how to create a Koch snowflake or a Koch star based on using algorithmic modeling. Okay, so this is an algorithmic modeling challenge, and this is the second part of the video where in the previous one I already explained how the algorithm works and what we're going to do, and I implemented it using vanilla Grasshopper. In this one, what I'm going to do is I'm going to use C# scripting within Grasshopper and Dynamo. Sorry, and let me start over again. Ho, ho, ho! Can you hear the bells? All right, so welcome to part 2 of this algorithmic modeling challenge, where we were trying to break down how to create Koch stars, this fractal shape. or Koch snowflakes, I think they're also called. In the previous video, I showed how the algorithm works and what are the steps that we were going to follow in order to create this algorithm, and I implemented it using vanilla Grasshopper, which is a visual programming language for Rhino, which is a 3D modeling environment. What I'm going to do in this video is I'm going to apply the same logic, but I'm going to implement it by using C# scripting within the Grasshopper environment. It's going to look something like this. It's just going to be basically a recursive algorithm that takes the polyline and applies the process of Koch subdivision over and over again, so that we can just choose how many levels of subdivisions we want to do, and the algorithm will just start subdividing this geometry. Okay, so very simple. It's like sort of like Christmas inspired, because Christmas is coming very soon at the time of this recording. So let's take a look at how this would work. Okay, let's get hands on. All right, so let me turn on noise reduction again. There you go. Okay, so now we should be, yes. Alrighty, so let's get ready for the next one, which is going to be, I'm just going to shut everything down here. I'm just going to create a new, alrighty. So what are we going to do? This one, what we're going to do is, it's going to be a 3-part. I had an idea this morning. So while I was having lunch, instead of doing 2 parts, Grasshopper and C#, from here on, I think I'm going to do 3 parts, which is going to be, first, I'm going to explain the concept and the algorithm conceptually. Then in the second video, I explain how to do it in vanilla Grasshopper. And the third one is going to be how to do it in C#. And then perhaps in the future, a 4th one can be how to do this in other platforms. But I already take the knowledge of what I have explained in the previous video. Okay, so I think and this is probably better, because then someone who wants to do C# can watch the first one and the third one. They don't have to dig through the Grasshopper one to, you know where I'm going with this. Okay, so, all right. And what do I want to say about this? All right, is there anything I want to say about all of this cellular automata? Okay. Oh, this is cool. We should do this at some point. Interesting. What is this, an interactive SVG? Ooh, cool. That's cool. All right. So, yeah, I'm getting distracted here. Okay. Let me draw. Nah, I'm going to talk about this first. All right, so let's get started. Let's start first with, what is a Sierpinski triangle? I'm not even sure if I'm pronouncing this correctly even, but Sierpinski triangles are basically a form of a fractal subdivision, which is basically taking any geometry, for example, a triangle, and then subdividing it into smaller triangles of its own. So for example, the algorithm would go something as what's going to show up here. So you would start with one triangle, and the second iteration, what you do is you subdivide each one of the triangles into 3 triangles, leaving the one in the middle typically empty. And then you keep doing that over and over for each one of the remaining triangles. So for each one of them, you subdivide it in 3. For the remaining one, you subdivide it in 3, etc., etc. And it creates this recursive fractal form of voids and full shapes, which I find super interesting, actually. So and I've chosen this because it's close to Christmas time and it looks like a Christmas tree of sorts, which is cool. And I also, digging through this, I also found that actually you can make this happen with pyramids and with tetrahedrons as well. So it could be really interesting to actually do this at some point in the future, maybe for a future algorithmic modeling, or maybe if you're watching this video, you just want to give it a try yourself and you want to post the results of your work in our Discord channel. Okay, so maybe we can do that at some point. But the algorithm is going to be very simple. It's going to be taking any geometry, for example, basically any polyline, for example, a triangle, and then finding a way to mix to create new polylines based on the points of the polyline and the middle points between those vertices of the polyline. Let's take a look. Let's actually break down how the algorithm would work with a little bit of a sketch, and then we move on into implementations on the following videos. All right, so it's drawing time. Okay, hey Arasto, what's up, man? So, okay, so let's draw a triangle. This one can be rather big, I think. All right. No, we want black. Okay. We want black and we want here, 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 and here. All right. And then the next thing that we want is we want here to say, well, we have vertices 0, we have vertex 1, we have vertex 2, and we have vertex 3, which is duplicated here. And then what we're going to do is we're going to find the middle points here, we're going to find the middle points here, we're going to find the middle points here, and those points are going to be, for example, what are they going to be? They're going to be M1 or M0. I'm just going to call it M0, M0, this is going to be M1, this is going to be M2, and then just very likely the only thing that we need to do is we need to make sure that we add a triangle. We need to make sure that we add a triangle that is formed by these 3. So 0, M0. Right. Let me do 0, M0, M2, and 3. We need to make so that's going to be 1. The next one is going to be this one, and it's going to be a triangle where we have 1, M1, M0, and 1 again. Actually, you know what? I'm going to go here. Where is my cursor here? Yes, I'm going to delete. How do I delete? This is not going to be 3. This is going to be 0. It's going to be 0. This is going to make things easier to it when I explain them afterwards. And then here I'm going to make this. This one is going to be 2, M2, M1, and 2. Yeah, I think that makes sense. All right. And this is just going to be fairly easy, right? and then just maybe I can do that in each one of the actual triangles. Why not? So maybe here I can just here, and here. I guess. And then for the next one, we could see how taking one, we can just take one and then just start repeating this over and over. Okay. All right. The algorithm for generating Sierpinski triangles is actually super easy. So we're going to start from a triangle, for example, which we're going to take in as polyline geometry. And as I typically say, polylines are nothing more and nothing less than just sequences of points. So if we think of a polyline as basically 4 points, as this polyline that has 3 segments, as 4 points, point 0, 1, 2, and then a third point, which is the same as point 0, but it's also on the list so that the polyline closes, okay? Then what we can do is we can start writing an algorithm that given any polyline, it finds intermediate points and it generates triangles so that in a way that takes into account how many segments are in that polyline. So for example, let's say that for each pair of vertices, 0, 1, 1, 2, and 2, 3, what I do is I find the middle point in that sequence. So for example, the middle point between 0 and 1, the middle point between 1 and 2, and the middle point between 2 and 3. Then once I have found those and having the original points of the polyline, then it actually becomes very easy to see that the first triangle is going to be just joining the point 0, is going to be just joining point 0, point M2, M0, and M1. I totally missed that one. Join vertex 0, vertex M2, M0, the one in the middle, join vertex M2, this one here at the center, and then vertex number 0 again. The second triangle is going to be very similar, and it's going to be just taking vertex 1 and joining it with M1, with M0, and with 1. And the third one is going to be taking vertex 2 and joining it with the middle point up to 3, the previous middle point, and back into itself. So you can see that it will boil down to creating polylines that perform a very detailed sequence, which is for each vertex that we have. For each vertex that we have, for example, we're going to join that vertex with the next middle point ahead of it, the previous middle point behind it, and then itself again. All right? So that's going to be super easy. And then once we have these 3 triangles, then what we can do is to apply more recursion and to keep going over and over again and apply this recursion. The only thing that we need to do is we now take the 3 triangles and feed them back into the system that creates subdivisions, so that for each triangle now we create the other 3 triangles generating 9 and generating 27, etc., etc. Okay? So it's going to be super easy, and what I'm going to do is, in the next 2 videos that are going to follow to this one, I'm going to implement this logic using Grasshopper, which is a visual programming language for Rhino, which is a 3D modeling environment. And then what I'm going to do after that is that I'm going to try to do the same thing, because Grasshopper is not going to let me do the recursion in a clean way natively. So what I'm going to do is I'm going to write the same algorithm using C# scripting within Grasshopper. Okay, so if you're interested in seeing how this works and how this can be implemented, make sure you check my next two videos, whatever you're more interested in, plain old Grasshopper or C# scripting within Grasshopper. Thanks a lot. See you on the next video. Okay, so I guess then I should record the introduction to this one. No, I can do that. No, I'm gonna have to do that by the end. Once I have, I need to do that by the end. Once I have actually done the homework. I've implemented both things in Rhino and in Grasshopper. So, all right. So, where are we then now? So I need to. What do I need to do? I need to fire. What am I going to do? What am I going to do? Oh, I see. And then here I have this. Okay. Mm-hmm. Mm-hmm. All right. So what is this going to look like? I'm not sure about if I divide the video in 3 parts. I'm not sure how to do the introductions and not in or whether if to just start right away. I should start with a tiny introduction where at least I'm showing what I'm doing. So, okay, I'm just going to start doing it. And then we will record a tiny introduction for this video. Then I will do C#. We will record a tiny introduction for C#. And then once we have everything, I will record the intro to the 3 videos. That's what I'm going to do. I wish, yes, exactly, Said, 1, 2, 3, but I'm thinking about like what to show at the intro for each one. That's what I am. So I think I want to finish. I think I want to start doing the Grasshopper one, finish that, and do like a tiny intro for the Grasshopper, and then the same for So we're going to do that. Okay. So yeah. Great. So let's get started. The first thing we're going to do is we're going to create a triangle, right? So why not? So let's do that. I'm going to click here on polygon. I'm going to click on number of sides to be 3, and then I'm going to just press 0 so that I start at the center, and I create this triangle that is going to have its first vertex all the way up here. And I'm going to press F7 to just remove the grid, which is not going to be very useful. I'm going to bring this here into Grasshopper. I'm going to set one curve, etc. And I'm going to drop a panel so that I can see what I'm working with, which is a reference polyline curve. That's great. And I'm also going to drop some bifocals so that those of you who are not icons persons, everyone has mistakes, I'm sorry. Those of you who are not icon people can at least read what the components are. So as I described in the algorithm, the first thing that we need to do is we need to figure out what are the end points. So what are the points of the polyline? And then once we have that, we need to figure out what are the middle points. What are the middle points? Oh, I drew a lot of. I drew a lot. Okay. I think I overdrew here. Oops. All right. I'm going to start over again. I'm going to start over again. Starting over again. I got confused. Yeah. Starting over again, all from scratch. Okay. All right. So, and here I have this. Okay. Great. Let's get started. So the first thing we're going to do is we're going to draw a triangle in Rhino. So I'm going to hit polygon. Number of sides is going to be equal to 3. And then I'm going to hit 0 so that I'm centered in the origin. And I'm going to just draw it here, for example. I'm going to press F7 to remove the grid, which I don't need. I'm going to create a curve parameter here in Grasshopper, set one curve, and I'm going to bring in this curve from Rhino into Grasshopper so that I can work with it. I'm going to drop a panel because I like having panels so that I can see what's going on in the wires. And then I'm just going to drop in here the bifocals plugin so that those of you who are not icon people, I'm sorry, everyone has mistakes. Just joking. But those of you who are not icon people, you can at least see what these components are. Okay. And so the first thing that we're going to do is, well, as per the algorithm that we were describing before, the first thing that we need to do is we need to extract the vertices from this polyline, okay? And then the second thing that we need to do is we need to figure out what are the midpoints, for each one of those segments of the polyline. And then after we do that, we will start cherry picking which ones we need in order to join them with polylines. Okay, so how can we do that? Well, for example, in order to extract the points in of this polyline, there's two things we can do. We can either take the control points, and therefore what we will end up is with a list of the 4 points. So that's one way to go. Another way to go is to explode the curve into individual segments so that what we end up with is with 3 line-like curves. And then for each one of them, we can just get the endpoints. All right. And the endpoints will give me a list of the 3 starting points and the 3 of ending point. Okay. I think this is probably what I want to do because I will also want to use the individual segments. So I will want to use the line-like curves to find the point at the center of those segments. So by the point at the center of those segments, I'm going to find by evaluating the curve. So I'm going to evaluate the curve at the center. So that's going to be each one of these curves. And I'm going to drop here a panel that says 0.5 because I want to find the point that is at the center. Now, remember that evaluate curve takes a parameter. And for lines, the parameter is a value that goes through the domain of the curve, which for straight lines is always going to be from 0 to 1. However, because with these lines in the polyline come from an explosion, they're not exactly lines, they're line-like curves, but they're still curves. And their domain can be whatever. So actually, if I query this, you can see the domain of these lines is from 0 to 25, whatever. So if I reparameterize, I turn it from 0 to 1. So this is what I want here. So I'm going to reparameterize at the input. And then I'm going to, so that I get the points at the center of those lines. So if I do that, now I get these points, a list of 3 points. And I can kind of start working with this already. So for example, What I wanted to do, if you remember, is, for example, for any given triangle, what I wanted to do was I wanted to say, let me find a polyline, let me create a polyline that joins this first point with the next middle point, with the previous middle point, and with the same point again. So what I need to do is, I need to create a polyline that joins 4 points that are ordered in that sequence. So in Grasshopper terms, what I will need to do is I will need to create a list of points that are those 4 points that I have there in that sequence, in that exact sequence. So what I will need to do is I will need to do a little bit of list management so that I'm able to create a list of 4 points that has those exact 4 points one after the other. How am I going to do that? Well, you can see that here I have the 3 starting points, so 0, 1, and 2. But I have them on the same list. So the first thing that I'm going to do is I'm going to graft this tree so that I have each one of those points in a different list. And therefore, to that list, I can start adding other points, such as, for example, the point here, the points that are in the middle, right? So for example, let me say that I'm going to merge this tree that I have here. I'm going to merge it with what's coming from the second one, all right? You can see that it doesn't work because the structure of what I had before, the structure of what's coming from this component is 3 branches, 0, 1, 2, whereas the structure of what's coming here is one single branch called 0, 0. So what I need to do is just basically go ahead and also graft this this list, so that it takes the same shape and the same structure as the first one. You see these two. And now when I merge this one with this one, then this point is going to go here just because it has the same branch. This point is going to go to this branch because they have the same branch, etc., etc. So you see, when I merge them together, points that are on the same branch, they get merged together into the same branch. So now it's very nice because we have 3 lists that we could use to create polylines with 2 points each one. So actually, let me try to start doing that. So I'm going to create a polyline with each one of the 3 lists. And you can see that I have a polyline that starts from this one to this one, another one that goes from this one to this one, another one that goes from this one to this one, and we have the first side of each one of the 3 triangles, which means we are on good track. Now, what is the next thing that I need to do? What I need to do is I need to say, well, the next thing that I should add here, the next point that I should add to each one of my 3 lists should be also a middle point, right? But it should be the one that is before each one of these, each one of the vertices. So if I was looking at vertex 1 and then I was adding the one after, then what I need to do is I need to add now the one right before. How is that going to work? Well, turns out I have a list of ordered middle. I have a list of point 0, 1, 2. I have another list of midpoint 0, 1, 2, the ones right after. So if I now want to add here another list to be combined with this tree, but what I need is, instead of these points in the same order, what I need to do is I need to point to the middle points that were before. So basically what I need to do is I need to take this list and change the order of these points so that all of them shift 1 position to the back. And by doing that, I will be able then to plug that shifted list into here and then have the same points, the same middle points, but added to the list with 1 position less. This is very tricky to explain. Let me show you how that works. I'm going to take this evaluate curve and I'm going to shift that list. All right? Shifting takes the whole list and moves all the elements 1 position or several positions up or down. So I'm going to take this and I'm going to say, I want to shift. So right now I'm shifting 1 unit. And what is happening is you can see that the elements are moving 1 position to the back, right? So 0 minus 7 was position 1 and is now position 0. 6, 3 was position 2 and is now position 1, which I think is kind of what we wanted. And also you can see that the wrapping is true, which means that the element that was first, instead of going back to -1 getting lost, what it does is it goes back to the end of the list, which is also the behavior that we want. So now I can just graft this tree so that it gets the same structure that all of the other ones has, except for the fact that, look, the structure is not identical. This has 3 levels and this one has 4 levels because it comes from an additional processing of the data. So if I were to now merge this tree, the one with 4 levels, into this one that has 3 levels, they would not merge correctly because now I have a bunch of different trees, branches in the trees that have different depths. One way to solve this is by making sure that this branch has the same amount of levels as the previous ones. What I could do is I could offset everything to the left, but I think there's actually a simpler solution, which is, you see all these zeros that I have here leading? Those are redundant. That is not information that I really need. So something that I can do is for each one of the previous branches, I can just go ahead here and simplify the tree so that I remove branches that are redundant and don't really contain information. If I do that for this one, I get 0, 1, 2, much cleaner trees. If I simplify this one here, I get 0, 1, 2, much cleaner. So now everything is 0, 1, 2. And if I clean it here, you now can see simplify. This becomes 0, 1, 2. And now everything is merged correctly into the same branches. And you can see that each one of my polylines is great now because it joins the vertex, the next middle point, and the previous middle point. Right? How awesome is that? The last thing that I need to do is to just duplicate again the same original point so that I close up the triangle. So I can just do that by saying, well, the same starting point, I'm going to add it again to the last one. Oh, and this is not working. Why is this not working? What did I do here? What? Oh. All right, sorry, I made a mistake. This was not working because, look, even though it looked like, before I joined this, it looked like each one of the polylines, each one of the triangles was this one and this one. And then this one and this one and this one and this one. But it turns out that when I bake it, all right, and I take, for example, this one, look, it's actually, the curve that I'm getting is actually this one instead of this one. And the other one is this one, and the other one is, yes. So it turns out that I was shifting the other way around. So I was shifting +1 instead of -1, which is what I should have done. So I'm going to shift the list in the opposite direction. So I think I now visually, I get the same thing. But if I were to bake this, and take them out and then ungroup them, so you would see that this is the right triangle, this is another right triangle, this is what I wanted to be getting. And then if I duplicate the last point now, you see that the triangles are now closed. And if I actually create a boundary surface around each one of these polylines, you can see that the triangle has already been done. Okay, so All right, so that's great. So what can we do? I'm going to clean up all these parameters. So yeah, it turns out that control points was not an interesting way to go. And check this out, how clean and how simple doing this subdivision has been with just a little bit of data tree manipulation. All right. Okay, let me save this so that it doesn't break, just like Sierpinski, so it doesn't break like in my previous video. So I'm going to group all of this. Okay, so this is the algorithm that takes one curve, okay, and then it takes one triangle or one polyline, and then it subdivides it into a bunch of triangles for that polyline. So what I'm going to do now is I'm going to try to apply recursion to this algorithm so that I'm going to try to subdivide each one of the triangles. The problem is that Grasshopper doesn't really let me perform recursion programmatically. Okay, I cannot create, because Grasshopper is a directed acyclic graph, which means that if I try to now plug the result of this back into the beginning so that I create a loop, you see everything breaks because I cannot connect the output of something into an input that will lead into the same output, creating a loop. All right, it's the part of how Grasshopper behaves. There are plugins that allow you to work around that limitation, but I'm not very interested in showing those at this point. I'm more interested in just the concept. The concept being, well, the way we would do this manually with simple Grasshopper, vanilla Grasshopper, is that we just simply take the whole thing, we copy paste it, and the output of the first subdivision, we just feed it into the input of the next subdivision. And then we get this family of triangles that conform the Sierpinski tree. And if we want 2 levels, we can do it. If we want a third level of subdivision, we can subdivide even more and then plug this here. If we want another level of subdivision, we can just plug this in here, add another layer, etc., etc. Right? And then we end up with as many levels as we can basically manually copy paste. This is one of the limitations that Grasshopper, this procedural environment, has right now. Okay. In the next video, I will show how to write, using scripting, how to write this same logic, but then be able to apply this recursion programmatically. All right. Another thing that I would like to highlight before I move on to the next video is everything that we have done here. We've done it for this nice equilateral triangle, but honestly, there's nothing in this algorithm that requires that the polyline that we work with is a perfect triangle. It doesn't even require the polyline to be a triangle at all, because everything that we have done is working assuming that we just had an input polyline as a sequence of points. So if I were to, for example, just draw a rectangle and feed that in as a curve, you can see that the division algorithm just works exactly the same. It just creates triangles for each one of the angles of the polyline. If I were to create a free form sort of polyline and then use that, it would also work perfectly. I would have this Sierpinski subdivision of this polyline. And also, super nicely, this is also not bound to 2 dimensions. So I can just take this polyline and I can start now messing with the vertices and make this polyline volumetric, give it depth. And then very interestingly, I get also Sierpinski subdivisions for each one of these segments, each one of the angles of the polyline, which I think it's pretty cool. So I think with this, I'm happy with the Sierpinski subdivision algorithm that we have programmed in plain old Grasshopper. Okay, and I'm going to go back to the triangle because, you know, it's nice. It's the Christmas tree kind of feeling. All right. Now, if you're interested in knowing how to implement all this logic, but instead of using components, we write the code inside a scripting component, and how to implement programmatically with a slider without the need to copy paste this 17 times, how to implement this recursion subdivision, then make sure you check my next video, okay? And if you like what you saw, hit a like, hit subscribe, etc., and all those things. All right, thank you very much. See you in the next video. All right. Exactly. Yes, we can use the Hoopsnake plugin, and I think there's the Anemone plugin, and I think there's a bunch of plugins that allow you to bypass this limitation. If any of you are interested in making a version of this that uses those plugins, I'll be happy to just post it on the Discord, and I'll be happy to put this as sample files in the repository where we have all the code. And make sure you put your name and your contact if you want to be properly credited for that. Okay. But yes. But yes, Said and Salvador, like I'm just not very interested in using plugins to solve problems. I'm more interested in teaching you how to solve those problems yourself. So that's why I want to write this implementation in with C# so that you can know how to actually do this. Okay. All right. So what we're going to do then is now I'm going to. So no, the intro to this video. Okay. I have to record the intro to this video. All right. Fine. I'll put this on again. All right. So hi, and welcome to the second part of this video where we are modeling again. Hi, woohoo, and welcome to the second part of this algorithmic modeling challenge where we are modeling a Sierpinski triangle, or what I'm going to call it a Sierpinski tree, which is basically a fractal subdivision algorithm that creates something like this. You start subdividing in triangles and recursively start more and more triangles, and if you fill them up, you have this like tiny Christmas tree that you can see here. This second part is going to be specifically about how to implement the algorithm of the Sierpinski subdivision using vanilla Grasshopper. Okay, and it's going to be a super simple. It's going to involve a little bit of data manipulation, which is always interesting. And we're going to hit the limitation that in order to perform the subdivision, Grasshopper by default, natively without plugins, cannot let you do that. So we will just have to copy paste the block that performs the subdivision as many times as subdivisions we need to do. All right. So, and then in the next video, I will explain to you how to write code to make this happen programmatically without all this copy pasting. Okay. But let's focus on the Grasshopper part. So let's figure out how to do this with vanilla Grasshopper. Alrighty, and it's C# time. Woohoo! All right, let me get ready. Now, actually, you know what? I didn't say that. In the previous video I explained the algorithm, and then in the second video I want to explain. All right, sorry, we're starting again. You just want to see me with the horns more, right? All right, we're doing this again. Oh. Hi, and welcome to the second video in this series. Blah, blah, blah. I think I've had too much coffee today. That might be the problem. Starting over. Ho, ho, ho! And welcome to the second part of this algorithmic modeling challenge video, where we are modeling Sierpinski stars or Sierpinski trees. Okay. In the first part of this block, I explain what a Sierpinski subdivision algorithm is, and then I explain the basic overall idea of how we're going to implement the algorithm. In this second video, I would like to show you that implementation by using vanilla Grasshopper, which is a visual programming environment that is attached to a 3D modeling environment called Rhino. Okay. What's going to be interesting is that it's going to be super simple to do. It's a very simple algorithm. It's going to involve a little bit of data manipulation, which is always interesting to learn and good thing to learn. But you will see very soon that we will hit one of the limitations of Grasshopper, which is that we cannot really perform recursion. So in order to do this nested subdivision algorithm, we will just basically have to manually copy paste the block that generates the subdivision as many times as levels we want to subdivide. All right, it's part of the limitation of how vanilla Grasshopper without plugins and without any additions work. In the next video, I will explain how to perform that recursion in a programmatic way, being able to control how many levels by implementing the same thing using C# scripting inside of Grasshopper. Okay, and all right, less talking and more doing. Let's get ready and let's get hands-on. All right, I'm much happy about that. All right, so I'm going to turn everything off now. And all right, and what I'm going to do is I'm going to plug in this curve here. And I'm going to start just with, I'm going to start just now the second video right away, okay? All right. And do I have here the sketch? Mm-hmm. Okay. All right, let's get started. So I have a triangle here in Rhino, which I just brought here into Grasshopper as a parameter. Okay, and then I'm just going to create a C# script component, and I'm going to customize the inputs. So the first one is going to be the polyline that I'm going to be subdividing with the Sierpinski algorithm, and then the second input is going to be how many levels of subdivision I want to perform. I'm going to add here a slider with an integer for how many levels I want to plug in, and I'm also going to plug in here the polyline. I need to make sure that I right-click on each one of the inputs and I specify the right type of input. For the first one is going to be polyline, and for the second one, for levels, is going to be the integer. All right, and I'm also going to customize the output, and I'm going to call this Sierpinski. Okay. All right, and then as I go in, I can double click here, and I'm already ready to start typing some code here. As usual, I also like having a output panel here, just for the sake of visualization, and a geometry wrapper so that I can visualize the output of this component. Also, I probably want to plug in here a panel to see what's going on, and I will probably want to have a boundary surface at some point here so that I can see as in a field way what is coming out of the algorithm of the component. Okay, and I think at this point we are ready to start typing some code. I want to review real quick what we're going to do. We have a polyline. The polyline is a list of points. Okay, and remember that what we were going to do is we were going to find the middle points between each pair of points in the polyline. And then what we were going to do is we were going to smartly, one by one, we were going to try to create new polylines that we're going to join for each one of the vertices. For example, vertex 1, we were going to join it with the middle point that was next to it, so the next segment, then with the middle point that was in the previous segment before it, and then back with itself. So this was the sequence that we were going to use for creating these polylines. So if that's the case, then what we're going to do is we're going to write here. First, we're going to start with a simple algorithm, which is taking one polyline and then subdividing it into the 3 triangles that form one Sierpinski subdivision. And then once we got that working, the next thing that we will do is we will implement a recursive algorithm that takes and performs this operation over and over again as many levels as we want over the previous results. Okay, so let's start with the basics. Let's start by writing the algorithm that takes one polyline and returns a list of polylines that are the Sierpinski subdivision. Hey, good afternoon, Rafael. Fernando, what's up? How you doing? All right. So what are we going to do? The function. Okay. You know me well at this point, and you know how I like creating functional components that rely on functions, and then I can like switch and exchange between my different programs. So what I'm going to do is I'm going to write a function that takes the polyline and returns a list of polylines, which are the subdivisions. So I'm going to call that Sierpinski subdivision, for example. All right, and then this function is going to take a polyline called Paul, for example, and I think that's it. I don't think it needs anything else to work. And I'm going to open and close parentheses. And remember that the return type of this function is not going to be a polyline, it's going to be a list of polylines, because for one polyline, the result is going to be 3, 4, or however many, I don't know. It's going to be like several polylines, several of these new triangles. So the result is going to be a list of polylines, all right? And if you want this to return an array of polylines instead, that also works fine, okay? I just happen to like lists. They're a bit more friendly and they're a bit more user-friendly in a way, okay? So what is the first thing that I'm going to do? I'm going to start by creating an empty list that is going to contain all these triangles that we're going to be subdividing the original polyline on. So I'm going to start by saying I'm going to create a list of polylines that I'm going to be subdivisions, all right, which I'm going to initialize to an empty list, all right, and an empty list of polyline components. All right, so I have this, and then what I would like to do is I would like to say, well, the first thing that I need to do is I need to go over each one of the vertices in my polyline and start performing the algorithm that I explained before. So what we can do is we can say, well, let's create a for loop where we go over all the vertices of the polyline. So pol count, but we're not going to go over all the vertices. If we have a polyline like this that has 4 vertices, I only want 3 triangles. So what I'm going to do is I'm going to start with triangle 1, vertex 0, vertex 1, vertex 2, but I will not need to use vertex 3. So that's why this is going to be the amount of vertices in the polyline minus 1. All right? And this is the for loop that I'm going to use. Okay? All right, cool. So the first thing that I'm going to do now is I'm going to say, like in the diagram, first of all, I need to create an empty polyline. And to that polyline, in order, I need to start adding the vertex that I'm looking at, the next middle point, the previous middle point, and then the same vertex again. So I need to first create an empty polyline and then add those 4 points in sequence. The way I'm going to do that is I'm going to create a polyline called PL that I'm going to initialize to empty. All right. Then to that polyline, the first element that I'm going to use is add the current vertex that we're checking. So to PL, I'm going to add, from the polyline, I'm going to add the vertex that I'm currently looking at with the for loop. So that's going to be pol, open square brackets, I, and close square brackets. Remember that I can do this because in Rhino Common, polyline classes allow me to use the square bracket notation to retrieve the points that form that polyline. Okay, so in a way, polylines in Rhino Common are like lists and like arrays. They behave a little bit like that. Okay, so I have that in the polyline. All right. So, and then the next thing that I need to do is I need to calculate what is the middle point between the vertex that I'm looking at. So for example, vertex number 1, what is the middle point between the vertex that I'm looking at and the next vertex on my list? All right. So how does that work? Well, the way we can do that is we can calculate what is that point. So I can say point 3D, and I'm going to say middle forward. The middle forward point is going to be equal to a point that is between the vertex that I'm at and the next vertex at half the distance. How do we calculate a point in between 2 points? Well, if you remember, we did geometry gem. In geometry gem number 7, we developed an algorithm to take 2 points and a relative distance between them and return the point at that relative distance between them. So if you're interested in how this worked, make sure you check that geometry gem. So what I can do is I can calculate the point between this one and the next one. But actually at this is going to be, what I'm going to do to make this a little cleaner, I'm just going to say point 3D, current is going to be polyline, is going to be the one that we're looking at. And point 3D next is going to be the polyline that we're looking at, I plus 1. All right, so retrieve meaningful points for this triangle. So the current is going to be I, next is going to be I plus 1. And then the current vertex is going to be, I'm going to add current, and then mid next is going to be a point relative between current and the next point, between the 2 points, at 0.5. All right. And then I'm going to add that to the polyline. Polyline add mid next. All right. Add middle points. So there's going to be more code here, but let's see if so far what we got is working well. It's going to do the job. So let's assume we find the other points, etc., and we have the complete polyline. At that time, once we have the polyline, what we want to do is we want to say subdivisions, and for this list, the list of subdivided polylines, I want to add the polyline that I just calculated here. Okay? And once this function has calculated all the subdivisions for each one of the vertices, then what I can do is I can return those subdivisions. I'm not finished with the algorithm yet. I just want to check my progress and see if so far this is working correctly. Okay? So I'm going to hit run, and I see that at least I have no error, so that's a good thing. The other thing is that nothing is happening because I implemented this function, but nobody's calling this function. So just for the sake of giving it a first run, I'm going to Sierpinski. I'm going to output, oh no, my keyboard is doing crazy things these days. I need to get a keyboard for Christmas. Sierpinski is going to be equal to the result. I'm just going to try the subdivision once, okay, and see if it works. If I do that, I hit OK, and I can see that I do have a list of 3 curves, and it looks like it looks like I have one here, I have another one here, and I have another one here. So this kind of corresponds to what I expected. For each one of the 3 vertices, I have a polyline that is joining that vertex with the next middle point. So I think we're good on that end. All right. So the next thing that I need to do is I need to continue this polyline and join it with the middle point in the previous. So how is that going to work? Well, what I can do is I can say, well, the next middle point that I need to compute is the one that is between the point that I am at, but not the next one. I need to compute with the previous one. So the idea would be something like this. I would do point 3D mid previous, and then it would be point along the line, and then if I have the previous point somewhere, it would be this thing, and then I would add that point, so mid previous. Okay, but I need to find this. I still don't have this, so I can go back here and say, well, let me add this to the list. So I'm going to say point 3D previous is going to be equal to the list of points in my polyline I, but instead of +1, this time is going to be -1. All right. So I have, if I'm iterating through the polyline from 0 to, in this case, 2, every point is going to be in position I. Next is going to be I+1, and the previous one is going to be I-1. All right. The problem with this is I'm going to run this, and I'm going to get an error. I'm going to get an index was outside of bounds, because think about this. I'm looking at all the points on my Sierpinski tree, and I've been using, for example, number 1 as an example. The problem is that if I, in the particular case of point number 0, you can see that when I'm in the first point of the polyline, then the current point is at position 0. Midpoint is here, but then the next point is number 1. But the previous one that I want to use is not -1. The previous one that I want to use is the value of 2 or the value of 3. Okay? So it just so happens that if I just say I-1, when I am in the first iteration of this for loop, this becomes -1, and there is no point in the polyline that has an index -1. So I get an error. So what I need to do is I need to add here a small exception or a small corner case. I need to account for that corner case. So what I can say is I can say I'm going to say, for example, I'm going to create the point. All right, and then I'm going to say if I equals 0, then that point previous should be equal to, if this is different than 0, then this should be I-1, what we had before. All right. However, if it is 0, then we will have to come up with something different. And what we will need to do is we will need to say, well, the previous one, instead of being poly I-1, it needs to be the last one on the list. So it needs to be polyline and the amount of elements that are in the polyline -1. Okay, so like the last element of the whole list of elements. I think this should actually be -2, but I'm not entirely sure. But it looks good so far. All right. So if I look at this, you can see 1, 2, 1, 2, and then 1, 2. So I think this is looking good so far. All right. And yes. And okay, so we got this. And then what do we need to finish this? We just need to add the same point again to the list. Close the polyline by adding the same point again. So remember, we said we start with the point that we're looking at, the next middle point, the previous middle point, and then the same point again. So we're going to go back here and say to the polyline, I'm going to add again current point so that we close the loop. And if I run this, nice. So it looks like this is working now. The polyline is closed. All right. And the boundary surface can also close this surface because now they are closed polylines. All right. All right, great. So it looks like the algorithm is working. We have now a function that, given any polyline, it returns a list of polylines that satisfy this Sierpinski subdivision logic. All right. Was this clear? Did it make sense? Huh? All right. So the only thing we need to do now is to write another function that basically loops through with this and performs the recursion so that we can perform this operation over and over again as many levels as we want. Let's see how would we do that. All right, let me take a break here, but by writing some comments, perform Sierpinski. Oh, there's a typo here. Sierpinski subdivision to a polyline. All right. And here, create. Oh, lights are off. Okay, I think I lost my key light. Let me hold on. let me plug it in. Give me a second. All right, it's back. And this, yes. Oh, what a bumpy day, huh? Hey, Rafael, how can you get so excited about recursion? I know, it's a fascinating topic. Okay. Well, in the same spirit that as we have done before, the way we probably want to do this is by creating a function that takes a polyline and takes how many levels we want to subdivide that polyline in, and then returns a list of polylines with all these subdivisions. So I'm going to call that function. I'm going to call it Sierpinski star, which is going to take a polyline pol as an input, and it's going to take an amount of levels as an output. And then the resulting type, what it's going to give me back, is going to be a list of polylines. All right. Now, how are we going to do this? Well, the way we're going to do this is going to be, actually, let me draw a diagram. Let me draw a diagram to explain that. Hold on. I'm going to draw the diagram here. So, how are we going to do this? So let's say we have all right, and so if we have three polylines, we had 4 polylines on a list, for example, right? The way we would do this is we would say, well, now one of them is going to be subdivided into 4, right? And then the others are also going to get subdivided. Here, the others are also going to get subdivided. All right. So all of these together are going to form a large list. Okay. But then after that, what we will do is we will just use that list again, and then to create more. And then we will have more of this. All right. I think that works. Probably. Yeah. Where is my mouse? Here. There you go. And here we go. So the way we're going to do this is that our algorithm is going to perform recursion over a list of polylines. So imagine this. If we start off with a list that contains, for example, 4 polylines, what we need to do is we need to go over each one of the polylines and say, for the first polyline, I'm going to perform the subdivision and I'm going to generate a list of polylines, right? I can store that somewhere, but then on top of that, now I can take the second polyline of the first list and generate all these subdivisions, and then the third one and generate all the subdivisions, the fourth one and generate all the subdivisions. And if I stack them all together, I can generate a second list, which is basically all of these subdivisions all together, one after the other. All right? What this means is creating the Sierpinski subdivision over a list of polylines generates another list which is longer and it has all the subdivisions of those polylines one after the other. And if I want to do this recursively, the only thing that I need to do is I need to say, well, this new list that I just created, this one here, the one that has all the subdivided polylines, I just now feed it back again into the start. And I use it now as the new original list that has more polylines that I also start feeding into the algorithm and start subdividing recursively over and over and over again. All right? So this is the fundamental of this kind of recursion that we're going to implement here. So how are we going to do that? Well, code-wise, the way it's going to work is going to be very simple. I'm going to create a list of polylines that I'm going to call triangles. All right? And I'm going to initialize it as empty. Okay? So that when I start the algorithm, I have nothing in that list. I start an empty list of polylines. Now, in order to get the algorithm going, I need to give it some initial information. So what I can do is I can say kickstarted with the original polyline. So what I can say is to the list of triangles, what I want to do is I want to add that polyline that has been given me as a starting point. And then after that, what I want to do is I want to kickstart this whole thing. So I want to kickstart saying, let me take the list of triangles, let me apply subdivision to each one of them, let me stack them together into a new list, and then let me fit that list back into the for loop and start over again. So the way we're going to do that is by saying, I'm going to write a for loop, which is going to iterate how many times? It's going to iterate as many times as levels I want to subdivide in. So I is less than levels and I plus plus. And then here, what I'm going to do is I'm going to create a new list that is going to contain all the subdivided triangles. So I'm going to create a new list, polyline, subdivisions, which is going to start also as empty. All right, I'm going to start it. Empty here, and then after that, what I'm going to do is I'm going to go with another for loop. I'm going to go over each one of the polylines that are in the original triangles that I start with, and I'm going to start subdividing them and adding them to this secondary list that I just generated. Okay, so with that, what I'm going to do is I'm going to say for each, instead of using a for loop, I'm just going to use a for each loop in this case. For each polyline P that is in the list of triangles. All right, so I have all the list of triangles. So for each one of these polylines, what I'm going to do is I'm going to create those subdivisions by calling the Sierpinski subdivision on that polyline. All right, so I take each one of the polylines, I subdivide it, and I get the resulting list of triangles, so the 3 triangles. And then what I do is I take these 3 triangles and I add them to my list. All right, so to subdivisions, I want to add range. Remember, when you want to add a list to another list, when you want to attach it, the way you do it is by adding the whole range. I'm going to add the range of subs. Okay, and that's it. With this for each, I go over each one of the polylines, I subdivide them in triangles, and I add those to the subdivisions. However, this is not enough. There's something that I still need to finish. And what I need to finish is what I was explaining before here, which is that once this would be the list of subdivisions, all right? And this would be the list of, so this is going to be, this is going to be triangles, and this is going to be subdivisions. In order to keep doing this iteratively, what I need to do is now, this arrow that I have right here, I need to make sure that the list that I just generated of subdivisions now becomes the list of triangles so that I can subdivide them again. And the way to do that is very simple. I just go here and I say, well, I have finished creating subdivisions. This is ready. I have all the subdivided. So the list that I was using, triangles, now whatever I had before, it doesn't matter because those were not subdivided. I want that list now to become the subdivisions list that I just generated, so that the next iteration of the for loop, I take triangles is not the original one that I created here, but the subdivisions that I calculated in the previous iteration. You see this? Once I'm done with that, then it's just as simple as returning the triangles that has this list of subdivided polylines. And now that I'm ready for this, I'm going to go here and say, well, what I want here for the output is not one subdivision anymore, is all these subdivisions. So levels. I'm going to call Sierpinski star here and levels. And it looks like there's no errors, but I can see 1 subdivision, 2 subdivision, yay, woohoo! So 4, 5, I'm going to crash my computer again. Oh yes, I'm going to do it again, of course. No, why? Why did I do this? Okay, no, it looks like we're safe. So let me delete this. 6, 7, 8, 9. You see, like now it's taking like quite some time to compute, but you can see that I can start zooming in here, and it's quite cool. Let me do 10. Yoo-hoo! You know? Alrighty. Okay, cool. What else? What else? Oh yeah, of course. So let me write here again some boundary surfaces because it's nice to see it visually. Um, as I said before in the previous video, this can be applied to any. So for example, I can set any other curve. So I can use a rectangle and I can subdivide this into Sierpinski trees, for example, with 6 subdivisions. That's also fine. All right. Or I can just use, let me disconnect this. Disconnect this. I can do set one curve. I can do any random polyline, even if that polyline is not planar. So even if it's spatial, I can still subdivide this with the Sierpinski algorithm, which is kind of cool. No? And you like this? All right. And I think with that, I am ready to wrap this up. Do I have anything else to say? I'm going to go back to. I'm going to set the this one again. All right. So I think with this, we're good to go. I hope this was fun and interesting, and you learned a lot about geometry and recursiveness and Sierpinski trees and fractals and all the cool, good stuff. And this will hopefully lighten your mood and warm you up for a cozy holiday and Christmas, etc., and all those things. All right. Maybe in the future I add more videos to this series, so we have like a 4th and a 5th video when I do Sierpinski trees in other environments like Unity, VVV, I don't know, some other place. Okay, but in the meantime, stay cozy, stay warm, and if you like these videos, make sure to subscribe, to follow our live streams, and all to like these videos, everything, all those YouTube things. All right. And somebody's pointing out, Saeed is pointing out on the chat right now, we may in the future at some point do this in 3D instead of sticking to 2D. That would be a really cool thing to do. Okay. All right. If you do that yourself, make sure to get in touch and share your work in the comments, in our Discord, etc. It will be really cool to see it. All right. Thank you very much. My name is Jose Luis, and see you on the next video. Alrighty, so I think it's about time to show this working now. Okay. Okay, so a small intro. This is going to be a small intro for the C# video. All right. Okay. And let me save this. Ho ho ho! And welcome to the 3rd video in this algorithmic modeling series, where we're learning how to model Sierpinski trees. Okay, and in the previous videos, we learned what a Sierpinski star, or what a Sierpinski fractal is. We learned the basics of how to craft the algorithm, and I showed how to implement that in vanilla Grasshopper. In this one, the way we're going to do it is we're going to write a C# script inside of a Grasshopper component that is going to perform the exact same operation, with the advantage being that now, because we can use recursion inside of this component, we can actually customize how many levels we want to subdivide this Sierpinski tree on. Okay. With a slider, and actually we can get really far. We can get all the way to 10, for example, and you can see how I can like zoom in all the way in, and it's kind of cool. And if I did more, I could even zoom in much more. But also at the same time, I can also set this for spatial polylines, you know, and I can have this like 3D Sierpinski pattern that is actually quite cool. for a spatial polyline. All right. So I'm going to show you how to do that recursion. And in order to do that, I'm also going to teach you a little bit of how to perform recursion with a bunch of lists together and how to nest them together, which is going to be super interesting. Okay. So if you like what you see, stay tuned and let's give it a try and see how to implement this. Okay. Let's do this. All right, I want to take a screenshot here. Wait. So where is the serpent? Let me here, and I will take a screenshot of it at some point. Yoo-hoo! All right. Thank you, Andres. Merry Christmas for you too. Have a good holiday. I still have to record the intro. I still have to record the intro to the intro to these videos. Wait. I'm going to mute this. All right. All right. This is going to be the intro for the original video, the one at the very first. Ho, ho, ho! Can you hear me? Oh, you can't hear the bells? All right. Ho, 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 and welcome to a new algorithmic modeling series. In this one, what we're going to do is we're going to learn how to model a Sierpinski tree. A Sierpinski star is basically a shape that it's a fractal curve that is conformed by the recursive subdivisions of triangles over and over, in a fractal way. Okay. I'm going to teach you in this series is going to be composed of 3 parts. In the first one, I'm going to explain what a Sierpinski tree is, this thing that you're seeing here. I'm going to explain at a high level how the algorithm to implement it works. And then in the second part, I'm going to show you how to implement it in vanilla Grasshopper. Grasshopper is a visual programming environment. It's an algorithmic modeling environment for Rhino, which is a 3D modeling environment, which allows very simple, very easy visual programming. The problem with Grasshopper is that it's going to be very simple and it's going to involve a little bit of data manipulation, which is great. But the problem with Grasshopper is that it doesn't embed natively without plugins. It doesn't embed a way to make recursion. So I'm also going to teach you in the third part of these videos, I'm going to teach you how to implement that recursion in a native way in Grasshopper by programming the same algorithm using C# scripting. So here we're going to write some code to perform that recursive subdivision so that now we can programmatically with a slider control how many subdivisions we apply to this Sierpinski tree. And similarly, I would also like to show you how this subdivision can be applied to any polyline. It doesn't have to be a perfect triangle. It can be, for example, a square, or it can even be any 3-dimensional polyline. Any polyline accepts this kind of Sierpinski subdivisions. All right. So, as I said, the first part of this video is going to be how this works and the algorithm. The second part is going to be Grasshopper implementation, and the third one is going to be C# scripting implementation. I hope this is going to be nice and fun. I'm doing this because it looks like a Christmas tree, basically, and at the time of this recording, we are ramping up into Christmas holidays, so I thought it was a fun thing to do. Okay, so less talking and more doing. Let's take a look first in this video at what Sierpinski trees are and how to write, how to design at a high level the algorithm that runs them. Alrighty. Okay, I think with that we're done here, no? Woohoo! Yes, I think we're done today for today. Um, let me save this. Let me save this. Um, where are we? No, streaming. Alrighty. Okay, so I have a little time for Q&A if you want to do some of that. But otherwise, if you're taking off already, as I said this morning, this is going to be the last computational live stream because I'm going to be a little busy after this, and I'm going to be traveling as well, so I don't have the resources to make these videos. But I think what we're going to do is that next week on Saturday, we're all the community, all parametric community, and everybody who's interested, we're just going to jump on a Zoom call, and we're just going to chat. We're just going to have a coffee together, half an hour, 1 hour, whatever we take, and we're just going to share experiences, what we're doing, what we're interested in, etc., and just be humans, and warm up for the holidays. Why not? So we may have a live stream next Saturday, which is only and exclusively going to be just hanging out, all of us, on a Zoom call, okay? With webcam on if you feel comfortable, without the webcam, whatever. And I think the way it's going to work is that we're going to have a Zoom link, which I will share on Discord. So if you are not with us on Discord, make sure to join to stay up to date here. And then if you want to make sure that you know what the Google Calendar also has notifications for the events that we throw. So I think the way it's going to work is we're going to have a Zoom call, and then that Zoom call is going to be live streamed into YouTube. But for the community, we're going to be able to jump on that Zoom call and chat and hang out, etc., and see how that goes. Okay. Otherwise, in the meantime, it was a pleasure. I'm very happy to see a lot of familiar faces again, and I guess if there aren't questions, Arasto is burning out his his laptop by doing 12 levels of subdivisions. If you just do the polylines, it's fine. It's the surfaces that take a lot of compute time. But yes, so in the meantime, if there's no questions, I also wish all of you, all the best happy holidays. Hope you can spend them with loved ones, whatever that looks like for you. And I will see you next week on the Zoom call. All right. Thanks a lot. Have a good evening and enjoy the rest of your weekend. Bye bye.